the most incredible facts about space travel. T.O. Fall, asleep too. Hello there, and welcome to Sleepy Universe Channel. Tonight, we'll drift together toward one of humanity's boldest endeavors: space travel. The moment we leave Earth's protective atmosphere, everything changes. The air we breathe vanishes. The ground beneath our feet disappears. Sound, wind, life, none of it remains. Only silence and infinite emptiness. Space does not care whether we survive, but we choose to go there anyway. We build rockets that burn hotter than stars. We train astronauts for impossible missions. We try to keep the human body alive, even in places where biology begins to fail. Space travel is not safe. It is not natural. It is not easy. It is bold. It is terrifying. And if we want to see what lies beyond, it is the only way. If these quiet journeys bring you comfort, please consider liking the video, subscribing, or leaving a thought below. It helps others find your way here too, one soul at a time. But for now, all you need to do is relax. Let your mind soften, let your breathing slow, and allow yourself to drift gently into rest. Let's begin. A spacesuit is actually a tiny spacecraft. A spacesuit is far more than simple clothing. It is a one-person spacecraft designed to keep a fragile human alive in an environment with no air to breathe, no pressure to hold the body together, and temperatures that can swing hundreds of degrees within minutes. Inside, every layer serves a purpose. The innermost layer wicks away sweat. The pressure garment wraps tightly around the body to prevent blood from boiling in the vacuum of space. The outer shell protects against sharp dust and tiny meteoroids. The helmet visor contains a thin layer of real gold to reflect harsh sunlight. Oxygen tanks are fitted into the backpack, along with a carbon dioxide removal system, fans, and cooling water that circulates through hidden tubes. A single tear in the fabric could be fatal. That's why every stitch is inspected again and again. To leave the shelter of a spacecraft or space station, astronauts must trust this portable world completely. It is a tiny bubble of Earth carried into the silence of infinite night. Astronauts grow taller in space. In the absence of gravity, the spine is no longer compressed by the body's weight. The vertebrae gently separate, stretching the spinal column by as much as several centimeters. This temporary height gain can feel incredible at first, like a long, slow stretch after a lifetime of hunching. But the effect comes with pain. Back muscles must adjust to their new length, and astronauts often experience discomfort or spasms during their first days in orbit. The increased height also slightly changes how the body moves in a pressurized suit or narrow sleeping bag. Once the astronaut returns to Earth, gravity takes hold again, and the spine gradually compresses back to its original shape. The sudden reversal can also be uncomfortable. Mission doctors study these changes closely because they reveal how space affects the skeleton, cartilage, and connective tissue. If humans ever build cities on Mars or large, rotating habitats in space. Understanding how the body adapts to different levels of gravity will be essential for long-term health. Space has a smell, and astronauts can describe it. No one can breathe in space, so it may seem impossible that it has a smell. Yet astronauts returning from spacewalks often report a distinct aroma clinging to their suits and tools. Some say it resembles hot metal. Others compare it to burnt steak or welding fumes. The scent is created when high-energy particles from the sun and cosmic radiation interact with the spacecraft's hull, creating reactive molecules that mix with oxygen inside. Once the airlock is opened, these particles never reach the human nose directly, but they leave chemical traces on surfaces exposed to the vacuum. Researchers are studying these effects to better understand how to protect sensitive equipment from long-term exposure. The scent of space is one of the few sensory bridges between Earth and the void, a reminder that even in silence, the universe leaves its mark. Your body starts losing bone almost immediately in microgravity. On Earth, bones stay strong because gravity constantly pulls against them. In space, that pull disappears, and the body reduces the minerals it normally sends to strengthen the skeleton. Astronauts can lose close to 1% of bone mass per month in orbit, which is far faster than the most severe cases of osteoporosis on Earth. Weight-bearing bones like the femur and spine weaken first. Calcium that once fortified bone tissue enters the bloodstream, eventually leaving the body through urine. This mineral shift can also strain the kidneys. To counteract the effect, astronauts exercise for hours every day using special machines that simulate resistance in zero gravity. Even so, some loss is unavoidable. Once back on Earth, it can take years for bone mass to fully return, and not every astronaut recovers completely. Learning how to prevent this weakening is one of the greatest challenges facing future missions to Mars, where travelers might spend years away from home. The sun looks completely different when you are outside Earth's atmosphere. From Earth, the sun appears soft and yellow because the planet's atmosphere scatters the most intense light. In space, the sun is a fierce white sphere, blinding and sharp-edged against perfect black. There is no sky to filter its glare, no air to turn sunlight into soft colors at dawn or dusk. Its heat arrives with no warning, and without protection, it can burn through metal, fabric, or skin in moments. Shadows in space are equally extreme. Pure darkness with no gentle fatting at the edges. This stark contrast affects how astronauts see depth and distance. It also changes how solar panels absorb energy and how cameras record images. Every space mission must plan around this raw light. It powers spacecraft, threatens electronics, and creates a constant hazard for unshielded humans. The sun in space is a reminder that Earth protects us in ways we rarely notice, wrapping us in a layer of atmosphere that softens the violence of starlight. Astronaut food must be safe for zero gravity. Food in space cannot crumble, leak, or spoil. A single crumb drifting into a ventilation fan can cause a system failure. A drop of soup could float into a control panel. To avoid these dangers, every meal is engineered with care. Tortillas replace bread because they do not shed flakes. Drinks are stored in sealed pouches and sipped through straws. Fruits and vegetables are irradiated to kill bacteria. Even salt and pepper must be dissolved in water so they do not fly away. Texture and flavor also change in orbit, so spices are often stronger than they would be on Earth. A blocked nose and shift in blood flow can dull an astronaut's sense of taste, making food seem bland unless it has extra heat or sweetness. There are no ovens or refrigerators, only warmers and vacuum-sealed trays. Cooking is less of an art and more of a form of engineering. Each dish is a miniature science experiment designed to nourish without taking risks. Sleeping in space requires strapping yourself down. There is no bed, no mattress, and no gravity to pull the body onto a surface. Instead, astronauts sleep inside padded cocoon-like bags attached to the wall or ceiling of the spacecraft. Without restraints, their bodies would drift aimlessly, bumping into equipment or other sleeping crew members. The sensation of weightlessness can confuse the brain during dreams, creating illusions of floating or falling. Some astronauts describe the experience as peaceful, while others struggle to rest without the familiar pressure of lying down. Lights are dimmed, but noise is always present. Fans, pumps, and occasional creaks from temperature changes in the metal hull. The sleep schedule must match Earth time, even though the spacecraft may see a sunrise every 90 minutes. Learning to sleep in this environment is a skill that takes days, even weeks to master. Space travel demands rest, but it offers none of the comforts we take for granted. Tears do not fall in space, they clump. Crying is different without gravity. Instead of rolling down the cheeks, tears form floating blobs that cling to the eyes, building up in a stinging pool that can blur vision. Even wiping them away is difficult because a cloth will just spread the moisture into smaller spheres. Tears can drift into the nose or cause irritation if they get trapped beneath a contact lens. The only way to clear them is to blink repeatedly until surface tension breaks and the moisture floats free. Emotional moments, allergies, and even dust from equipment can trigger tears. The strange behavior of liquids in space is one of the first experiments children try to imagine, and astronauts live it every day. The human body evolved for gravity. In space, even the simple act of crying becomes a reminder of how far from home we truly are. Spacewalks are one of the most dangerous things astronauts do. When an astronaut leaves the safety of an airlock and steps into the open void, every danger becomes real. One tiny tear in the suit could mean death in seconds. Temperatures can swing from blistering heat to freezing cold as the body moves in and out of sunlight. The slightest force can send a person drifting away from the spacecraft. So every move is anchored by tethers. Even breathing is risky because the suit's atmosphere must be perfectly balanced to avoid oxygen toxicity or carbon dioxide buildup. Tools must be carefully secured, and every motion rehearsed again and again in underwater training tanks on Earth. Despite all the preparation, spacewalks always carry unknowns. The silence that surrounds an astronaut during a spacewalk is not peaceful. It is the silence of a place where life does not belong. There is no up or down in space, and the brain must adjust. In microgravity, the inner ear loses the sense of balance that helps people stand and walk. The brain, suddenly cut off from this steady flow of information, must build a new way to understand orientation. Walls, floors, and ceilings have no meaning, so astronauts often feel disoriented or upside down even when floating upright. Some adapt quickly. Others experience confusion, nausea, or dizziness for days. Simple tasks like reaching for a toolbox or turning a corner inside a spacecraft can become mental puzzles until the mind reorganizes itself. Objects no longer fall when dropped. Muscles no longer stabilize the body automatically. Every movement must be relearned with care. This shifting sense of reality is one of the most profound psychological challenges of life in orbit. Learning to let go of gravity does not just change how the body moves, it changes how the mind feels at home in the world. Space radiation can damage DNA. Outside the protective blanket of Earth's magnetic field, the human body is constantly bombarded by cosmic rays, solar particles, and high-energy atoms traveling at incredible speeds. These particles can pass through skin, tissue, and even metal, slicing through the DNA inside cells and leaving behind broken strands or mutations. On Earth, our atmosphere shields us from most of this danger, but in space, astronauts receive radiation doses far above the levels considered safe for long-term health. The damage can lead to increased cancer risk, weakened immune function, and even clouding of the eyes. Engineers are developing better shielding for future spacecraft and habitats, but protecting the human body from invisible particles that arrive from every direction is a complex challenge. Space radiation is one of the biggest barriers to deep space missions. Every day in orbit reveals more about a danger that follows astronauts wherever they go. Even simple fires behave strangely in zero gravity. A flame on Earth flickers upward, shaped by rising hot air and falling cool air. In space, there is no upward or downward motion because there is no gravity. Flames burn as ghostly blue spheres, floating in place and consuming oxygen slowly and evenly. Without buoyancy, smoke does not rise. It simply accumulates in confused clouds. Fires burn less intensely, but can be harder to detect and extinguish. A small flame in a corner of a spacecraft can silently fill a room with toxic gases before alarms even register the change. For this reason, every material on board, from insulation to electronic wires, must be tested for how it reacts to fire in zero gravity. Fire drills are designed to teach astronauts how to seal hatches, shut off ventilation, and locate extinguishers in darkness and confusion. Fire on Earth is dangerous, but fire in space is an unpredictable enemy that moves in all directions at once. Astronauts must exercise every day to stay alive. The muscles and bones of the body rely on gravity tugging at them constantly. Remove this force, and the body begins to weaken astonishingly fast. Without exercise, an astronaut's leg muscles can shrink, heart strength can decrease, and the ability to stand or even breathe comfortably back on Earth can vanish. To fight this, astronauts engage in daily workouts that last several hours using machines that create artificial resistance. One machine pulls against the body with elastic cords to mimic weightlifting. Another uses spinning cycles and tethers to simulate running. These workouts are not optional. They are as essential as eating or sleeping. Scientists continue to study how to keep the body strong for missions that could last several years. Otherwise, the first humans to walk on Mars might arrive too weak to stand. Metal can fuse together in space without heat. On Earth, metal objects rarely merge unless they are melted or carefully welded. In space, bare metal surfaces can bond instantly through a process called cold welding. Without any oxygen or moisture acting as a barrier, atoms from one metal object can slide into place against another, creating a seamless join. This effect can occur with tools, spacecraft parts, or even tiny fragments of debris. Engineers must coat or paint metal surfaces that might accidentally touch, or they risk equipment becoming stuck together permanently. This invisible force is not only fascinating, it is important. Without protective layers, a robotic arm might seize, a satellite panel might fail to unfold, or a hatch might refuse to open. Cold welding is a reminder that in the vacuum of space, natural rules change, and even simple contact becomes a science of its own. Microgravity changes how we taste food. Food that tastes rich and savory on Earth can seem dull or faint in orbit. The shift is partly physical. Without gravity, fluids pool in the upper body, creating a constant sensation of being slightly congested. This reduces smell and taste sensitivity. At the same time, the brain recalibrates its senses, adjusting to a world where the body feels suspended. To cope, astronauts often crave bold flavors. Spicy sauces, tangy fruit drinks, and foods with intense aroma. Classic comfort dishes sometimes taste bland or muted, while unexpected favorites like shrimp cocktail with extra horseradish become highly requested. This shift in taste is not just about pleasure. It is connected to appetite, nutrition, and morale. Long missions require food that nourishes both body and spirit. So space menus are carefully tested to work with altered senses. In orbit, even a simple bite carries the science of human adaptation. Space sickness is like seasickness, but worse. The human balance system is built to interpret gravity, motion, and body position. Remove gravity, and the brain receives strange and conflicting signals. Eyes see a stable environment, but the inner ear senses freefall. This mismatch can cause nausea, vomiting, dizziness, and disorientation. Space sickness strikes many astronauts during their first days in orbit, sometimes making it hard to work, eat, or even sit comfortably. Medical teams prepare for this with medication, careful meal planning, and slow introduction to physical tasks. Eventually, the brain adapts, but the early period can be unpleasant enough to ground missions temporarily. Returning to Earth can trigger a second wave of sickness as the body readjusts to weight and balance. Space sickness is a reminder that even when we leave the planet, we carry a body built for Earth. You can see shooting stars inside a spaceship when tiny particles of dust or micrometeorites strike the exterior of a spacecraft at terrifying speeds. They release a burst of energy that can create glowing streaks of light visible from inside. Astronauts sometimes witness these flashes while looking through darkened windows, or even when resting in dim corners of the station. These shooting stars are not harmless. Each one is a collision happening faster than any bullet. They carve microscopic craters into glass and aluminum, slowly wearing down the spacecraft's shell. Missions track regions of heavy debris and adjust their paths to avoid the densest fields. Yet the phenomenon is humbling. Even within the walls of a spacecraft, humans remain connected to the cosmos, watching sparks of ancient dust ignite against their fragile metal shelter. Growing plants in space is hard, but not impossible. Plants evolved under gravity with roots that grow downward and stems that reach upward toward the sun. In microgravity, these directional cues disappear. Water does not settle into soil. Air pockets do not rise. Seeds may sprout in unpredictable directions. Yet, with careful design, astronauts have learned to grow lettuce, radishes, and even flowering plants in orbit. Special chambers provide artificial light, nutrients delivered through mist or gel, and fans to move air around the leaves. Growing plants is more than a scientific curiosity. It is a test for future colonies on the Moon or Mars, where humans must produce fresh food and recycle oxygen. Watching a seed sprout among the stars provides both nourishment and hope, reminding astronauts that life does not belong only to Earth. Your blood moves differently in space. On Earth, gravity pulls blood into the lower body, and the heart works steadily to pump it back up. In space, blood floats evenly through veins and arteries, accumulating in the chest and head. Faces appear puffy, legs become thinner, blood pressure changes, and the heart does not need to work as hard. Over time, the heart itself can begin to shrink, losing muscle mass that must be rebuilt after landing. Doctors monitor circulation constantly and study how to prevent dangerous clotting or low-pressure fainting when astronauts return to gravity. This shift in blood flow affects everything from vision to temperature regulation. It might seem invisible, but every heartbeat becomes a story of adaptation. There is no such thing as absolute silence in a spacecraft. Space itself is silent, but the inside of a spacecraft is never quiet. Fans move air through filters, computers hum, pumps and valves click and whir. The constant vibration and airflow are necessary for life support, yet they create a soundscape that never fades. Astronauts must sleep, work, and think within this ongoing mechanical murmur. Over time, the noise can become a kind of background comfort, a reminder that the systems keeping everyone alive are still running. But when an unexpected sound is heard, like a new rattle or tone, it can cause instant alarm. Silence inside a spacecraft is not peaceful. It is terrifying because it may mean something has stopped working. The rhythm of machines becomes a heartbeat for the crew, marking time in a world without wind or birdsong. Some viruses become more infectious in space. In the strange and shifting environment of space, even microscopic life changes its behavior. Scientists discovered this when samples of viruses, including herpes and Epstein-Barr, were sent to orbit as part of medical studies. In the absence of gravity, under constant radiation exposure, and without the familiar pressures of Earth, some viruses become more active. Their genetic instructions can shift, making them replicate faster or reactivate from dormancy. Astronauts with no symptoms on Earth have sometimes shown signs of viral reactivation in space. This happens even when their immune systems appear normal by Earth standards. Space stress, altered sleep cycles, and fluid shifting in the body all weaken the ability to fight infection. This discovery has serious implications for future missions that may last months or years. Understanding how microbes change in space is crucial to keeping humans healthy far from home. In the end, even the smallest organisms remind us how deeply Earth's environment supports life in ways we barely notice. We use floating water bubbles to wash in space. Taking a shower in space is impossible because water does not fall. Instead, it forms drifting globes that can float around a room like tiny liquid planets. To stay clean, astronauts squeeze small amounts of water or rinse-free soap onto their skin and gently wipe with towels. Shower-style devices were tested in early missions, but they sent droplets flying into wires and fans. Even hair washing is a choreography. Water is massaged into the scalp and absorbed back into a cloth or allowed to evaporate into the air filters. Every drop must be reclaimed because water is far too precious to waste. This careful routine is not just about hygiene. It is about comfort, identity, and sanity during long missions. Simple acts like washing the face or brushing teeth take on new weight when every molecule matters and the body floats in a world of recycled air. Cleanliness becomes a practice in adaptation. The moon's dust could destroy a spacesuit. Lunar dust is not like the soft, rounded grains of beach sand on Earth. It is sharp, jagged, and formed by billions of years of meteor impacts, with no wind or water to wear it down. when it sticks to a spacesuit, it works its way into fabric and joints, damaging seals and scratching visors. During the Apollo missions, astronauts returned to their lander covered in dust that smelled like burnt gunpowder. It irritated their lungs, clogged filters, and clung to every surface. Future moon missions will last far longer, which means dust must be managed on every suit, tool, and habitat before airlocks are opened. Engineers are designing special coatings and electrostatic systems that might repel dust or shake it loose. Lunar dust may seem harmless, but it is a silent, ever-present threat, ready to tear through the suits that protect human life in a place with no air to breathe. Haircuts in space require vacuum cleaners. In microgravity, hair does not fall to the floor. Every snip produces strands that drift through the air, some finding their way into eyes, lungs, or delicate instruments. To prevent this, astronauts use special clippers with powerful vacuums attached, sucking cut hair into a sealed container before it can escape. The process is slow and awkward, especially in the confined quarters of a spacecraft. Mirrors are mounted on walls, but every tool must be tethered to prevent it from floating away. Even with precautions, stray hairs sometimes appear, caught in corners or drifting like tiny comets. Grooming in space is not a luxury. It is a necessity. Feeling clean and cared for helps maintain mental health in a stressful environment. And even the ritual of a haircut becomes a small reclaiming of normal life. It is one more reminder of how basic moments become extraordinary once we leave Earth behind. Astronaut gloves make every task harder. A spacesuit glove is a marvel of engineering with layers that protect against vacuum, thermal extremes, radiation, and micrometeorite impacts. But those same layers make the fingers stiff and clumsy. Fine motor work like turning bolts or adjusting wires during spacewalks can feel like threading a needle while wearing thick winter mittens. The gloves must also maintain internal pressure, which makes them push back against every movement. Hours of gripping and manipulating tools can leave astronauts with bruised nails, blisters, or even lasting joint pain. Engineers are constantly working to improve flexibility and dexterity, experimenting with new materials and pressure systems. Every gain in comfort and control makes spacewalks safer and more efficient. But the core challenge remains. Space is not built for hands. Every time an astronaut reaches out into the void, the gloves become a reminder of the fragile human body inside. We have lost tools in space, and they become tiny satellites. During spacewalks, astronauts work with hundreds of items: wrenches, cameras, clamps, tethers, and more. Despite careful planning, a few tools slip away, escaping into open space. Once free, they do not fall. They become tiny satellites orbiting Earth until they eventually burn up in the atmosphere. One astronaut famously lost a full tool bag, which drifted for months and could be tracked with binoculars from the ground. These objects are harmless on their own, but space is already filled with debris from past missions, old satellites, and fragments from collisions. Each stray object travels at tremendous speeds and could puncture a spacecraft if it crosses the wrong path. Every mission today adds to a growing cloud of human-made space junk. Even a lost screwdriver can become a threat. Space is big, but orbits are crowded. Keeping track of every object, no matter how small, is a constant challenge for mission control and the future of exploration. Every breath on Mars will have to be manufactured. Mars has an atmosphere, but it is almost entirely made of carbon dioxide with only traces of oxygen. The air is so thin that even with a full breath, the lungs would take in almost no usable gas. For humans to live there, every molecule of oxygen must be produced using machines that split carbon dioxide or pull resources from frozen water beneath the soil. These systems must run constantly without fail, and they must do so in an environment that freezes pipes, clogs filters with dust, and pummels equipment with radiation. Future Mars habitats will need backup systems, emergency stores, and repair materials to handle inevitable breakdowns. Plants may someday help with oxygen production, but they will not be enough on their own. On Mars, breathing becomes a technology, not a birthright. Every inhale would be a triumph of science over nature. The first human to set foot on Mars may never return to Earth. A journey to Mars takes many months, and once there, the planet's gravity, radiation, and distance create challenges that go far beyond existing return technology. The rocket fuel needed to launch from the Martian surface must either be brought from Earth, taking up impossible amounts of space, or manufactured on the planet using local resources. Even then, the journey home would take just as long. Some mission plans suggest that the first explorers may stay permanently, building habitats, growing food, and becoming the first settlers on another world. Returning home after years of low gravity and radiation exposure might be physically devastating. Bones, muscles, and organs could struggle to readapt. The decision to go to Mars might be a one-way choice, not because we cannot bring someone back, but because they would not survive the process. Mars may someday become a new cradle of humanity, but it may require pioneers willing to stay forever. Rocket fuel burns faster in space. On Earth, rocket engines fight against the pull of gravity and the resistance of the atmosphere. In space, with no air and no drag, they can burn more efficiently and reach higher speeds in shorter bursts. But this efficiency comes with risk. Without air, flames behave differently, and fuel must be mixed with its own source of oxygen to ignite. If anything goes wrong, the explosion has nowhere to vent. Every burn must be calculated with precision, adjusting the spacecraft's path by fractions of a degree to reach distant targets. Spaceflight becomes a delicate dance between power and control. Each ignition is a moment of commitment, sending a fragile craft hurtling through a vacuum that offers no chance to stop or slow down. The faster rockets burn, the more exact the math must be. There is no margin for error when the stars are the only road. Spacecraft must withstand temperatures hotter than lava and colder than Antarctica. In sunlight, a spacecraft can heat to temperatures that melt metal. In shadow, it can freeze solid in minutes. There is no air to carry heat away or keep it in. Only the raw emptiness of space absorbing or reflecting energy. To survive, spacecraft are built with thermal blankets, layered insulation, and radiators that can channel heat away like artificial skin. Electronics must stay within narrow temperature ranges or they fail. Water must not freeze or boil in its pipes. Even the spacecraft's orbit can determine its temperature as it moves into and out of sunlight dozens of times a day. These swings are violent, but the materials are designed to expand, contract, and endure. Every mission begins with an engineering battle against a universe that does not care whether metal cracks or a circuit overheats. Space is a place of extremes, and every machine we send must be ready to face both fire and ice without pause. Mars' sunsets are blue. On Earth, the atmosphere scatters sunlight in such a way that the sky turns blue, and sunsets glow orange and red. On Mars, the opposite happens. The thin Martian air is filled with fine dust made of iron-rich minerals. These particles scatter the red wavelengths of sunlight away and allow the blue wavelengths to slip through more directly. As the sun dips toward the horizon, the sky around it fades into a soft blue halo, while the rest of the sky stretches into warm tones of butterscotch and rose. Because the atmosphere is so thin, the colors are subtle, almost dreamlike, like a watercolor painted by a quiet universe. Future astronauts may one day stand on Martian soil and watch these gentle blue sunsets, knowing they are seeing a sky no human eyes ever witnessed before the space age. It is a vision that reminds us how different worlds can be, and yet how beautiful every corner of the cosmos is, each in its own strange and silent way. Space junk is one of the biggest threats to space travel. Earth's orbit is filled with abandoned satellites, fragments from old rockets, paint chips knocked loose during collisions, and even lost tools from spacewalks. These pieces are moving at incredible speeds, faster than rifle bullets, and each one is a potential disaster waiting to happen. A tiny shard of metal, the size of a grain of sand, can puncture a spacesuit or shatter a spacecraft window. Larger chunks could destroy entire vehicles. The more objects that collide, the more debris they create, leading to a growing chain reaction that scientists fear could someday trap us on Earth. This phenomenon, called a debris cascade, would make some orbits unusable and turn others into deadly fields of shrapnel. To protect astronauts and equipment, space agencies track thousands of objects in real time, adjusting missions to dodge incoming fragments. Engineers are designing new methods of cleanup, but the problem grows faster than the solutions. Space is vast, but orbits are not. Every launch adds to the risk, and every mission must navigate a sky that grows more crowded each year. astronauts train underwater to prepare for space. A massive pool called the Neutral Buoyancy Laboratory sits near Houston, filled with millions of liters of water and containing a full underwater mock-up of the International Space Station. Here, astronauts don spacesuits weighted just right to mimic the sensation of weightlessness. Every movement is slow and deliberate. A single kick or push can send a body drifting off course, just like in orbit. The water resists motion, but also supports the astronaut's weight, providing the closest simulation of working in zero gravity without leaving Earth. Underwater trainers rehearse every bolt turn, every panel connection, and every emergency response. It is a grueling, hours-long workout that leaves muscles shaking and minds sharpened. The pool is not just practice. It is preparation for life in an environment where dropping a tool means losing it forever, and where even simple tasks can feel like solving puzzles in slow motion. The underwater world becomes a doorway to the stars. Time passes differently in orbit. Einstein predicted that time is affected by motion and gravity, and space missions have proven him right. Astronauts aboard the International Space Station orbit Earth at incredible speeds, experiencing slightly less gravity than on the ground. Because of this, time for them moves just the tiniest bit faster. They age a fraction of a second less than people on Earth during their missions. The difference is small, nearly impossible to notice in a human lifetime, but measurable with precise clocks. If we ever send humans to the far reaches of the solar system or beyond, the effect will grow stronger. A traveler journeying for decades at near-light speeds would return younger than those left behind. Time itself bends and stretches as we move through space. The universe is not a single clock ticking steadily, but a collection of rhythms shaped by motion, mass, and gravity. Every orbit is a lesson in physics and a reminder that our senses do not always match reality. Cosmic rays can create light flashes in astronauts' eyes. Some astronauts, while resting in dark spacecraft cabins, have reported seeing flashes of light even with their eyes closed. These phantom sparks are caused by cosmic rays, high-energy particles from distant stars, supernovae, and black holes that travel across the universe at speeds approaching light. When these particles pass through the body, they sometimes strike the retina or optical nerves, triggering flashes or streaks of brightness that seem to appear out of nowhere. The effect can happen at random and makes sleep in space more unusual than on Earth. Scientists study this strange phenomenon to understand how radiation affects the human body and brain. If future explorers travel to places with even higher radiation exposure, like the moons of Jupiter or deep interstellar space, these brief sparks may become constant companions. The universe sends reminders of its hidden forces, even in the darkness behind closed eyes. Our bones could turn fragile on a long Mars mission. A journey to Mars could take more than a year each way, followed by months spent living on a planet with weaker gravity than Earth. During that time, astronauts' bones would steadily lose density, sometimes at a rate faster than any disease on Earth. Without gravity pulling down, cells that normally strengthen bone tissue begin to shut down. Minerals are carried away into the bloodstream and eventually leave the body. Even with daily exercise, the loss is only partially slowed. Once back on Earth, recovering bone strength can take years, and complete recovery is not guaranteed. If settlers remain on Mars permanently, their bones may adapt to the weaker gravity, growing lighter and more brittle over generations. The challenge of bone loss is one of the greatest medical barriers to deep space travel. It forces us to rethink not just how we move through space, but how we build bodies that can thrive in places far removed from Earth's familiar pull. Every tool on a spaceship needs a tether: a wrench, a pen, a toothbrush, or a camera. In space, every object floats freely the moment it leaves a hand. A lost tool can drift into a vent, block an air filter, or hover unnoticed until it collides with something important. During spacewalks, the danger is greater. A single tool escaping an astronaut's grasp can travel forever in orbit, becoming a piece of space debris. To prevent chaos, every object is clipped to a suit, a wall, or a looped cable. Tools are labeled, docked, cataloged, and counted. There is no such thing as casually setting something down. Living in microgravity means relearning how to interact with every object we use. A floating screwdriver is a reminder that space is not built for human habits. The world must be tied down, one item at a time. Space toilets use air instead of water. Without gravity, water does not fall and waste does not settle. That means a traditional toilet cannot work in space. Instead, astronauts rely on systems that use airflow to gently pull waste away from the body and into sealed containers. Solid waste is compressed and often stored for eventual disposal during re-entry. Liquid waste can be purified and recycled into drinking water through complex filtration. It is a process that must be constant, reliable, and carefully managed, because a malfunction would create a disaster in the limited space of a spacecraft. Using the toilet in orbit requires training, patience, and accuracy. Every part of the system must be cleaned and maintained. In space, even the private moments of life become exercises in engineering and adaptation. It is not glamorous, but it is essential for survival. Solar storms can endanger every mission. The sun does not always shine steadily. Sometimes it erupts with massive bursts of energetic particles called solar storms. These storms can blast through space at incredible speeds, striking spacecraft and planets with dangerous radiation. On Earth, our magnetic field protects us from most of this energy, but astronauts are vulnerable. During a strong solar storm, radiation levels inside a spacecraft could exceed safe limits within hours. Crews must quickly move into shielded areas, often constructed around water tanks or food supplies, which provide extra protection. Electronics are also at risk, since high-energy particles can short-circuit circuits and damage navigation systems. Plans for missions to the Moon or Mars must include emergency shelters and warning systems to predict when solar storms are coming. The sun gives life to our world, yet it also holds the power to threaten us as we explore beyond it. You can run around the moon's entire horizon in minutes. The moon is smaller and less massive than Earth, which gives it a weaker gravitational pull and a much shorter circumference. A person wearing a spacesuit with enough practice and stamina could run fast enough to complete a full circuit of the moon's visible horizon in just a few minutes. Each step would send the runner bounding in slow, high arcs due to the low gravity. The horizon would seem strangely close, curving more dramatically than on Earth. With each leap, the black sky would loom above, filled with stars even at midday. It would not be an easy run, since the uneven terrain and bulky suit add challenges. But imagining the feat reveals just how different the moon is compared to the world we know. It reminds us that every place in space holds new ways of moving, seeing, and experiencing reality. Even a run becomes something wondrous. Spaceships must carry their own atmosphere. Unlike Earth, where air surrounds us effortlessly, a spaceship must bring every breath along for the journey. The atmosphere inside a spacecraft is carefully engineered, a balanced mix of nitrogen and oxygen that mimics Earth's air. Carbon dioxide scrubbers constantly remove exhaled gas before it reaches toxic levels. Humidity must be controlled, so water does not collect on surfaces and short out electronics. Even temperature and pressure must be tracked carefully, because a single leak could cause the air to escape into the vacuum of space. Every system that supports the atmosphere has backups, and even those backups have emergency modes. Astronauts also carry emergency oxygen masks and suits in case of sudden depressurization. When future missions build habitats on the moon or Mars, these artificial atmospheres will grow into entire indoor worlds, complete with weather, seasons, and airlocks like gateways between Earth and alien landscapes. The air within a spacecraft is not a given. It is a fragile gift that we must build, protect, and renew every moment we are far from home. The International Space Station never stops falling. It may look like the International Space Station is floating, but it is actually falling toward Earth at all times. It stays aloft because it moves forward fast enough that, as it falls, the planet curves away beneath it. This creates a state of continuous freefall, which we call orbit. Inside, astronauts feel weightless because they are falling too, always missing the ground. There is no sense of acceleration, only a gentle drift that makes everything float. To stay in place and avoid crashing, the space station periodically fires booster engines or receives pushes from visiting spacecraft. Without these adjustments, the thin upper edge of Earth's atmosphere would gradually slow it down. This constant fall reveals a deeper truth about space. Gravity is everywhere, even far above the clouds. Orbit is not the absence of gravity. It is the art of falling forever while racing around the world at incredible speed. You can smell the Milky Way through a telescope. Some telescopes do not just see light, they detect radio waves and chemical signatures from clouds of gas and dust between the stars. Among these signals are molecules like ethyl formate, the same compound that gives raspberries their scent. Other clouds contain signatures of alcohol, carbon rings, and even organic molecules that might form the building blocks of life. By translating these signals into sensory forms like smell, scientists can get a glimpse of what our galaxy might be like if we could walk among its clouds. The Milky Way is filled with everything from bitter molecules formed in dying stars to sweet compounds floating near newborn suns. These smells are never breathed directly, but they hint at the strange chemistry of the universe and the shared ingredients between distant nebulae and life on Earth. Astronomy in this way becomes all of science combined, not just a view, but an invitation to taste, touch, and smell the cosmos through the tools we build. Time dilation could affect future deep space travelers. Time is not the same for everyone. According to Einstein, the faster you move or the stronger the gravity around you, the slower time passes. Astronauts aboard the International Space Station age slightly less than people on Earth because of their speed and the weaker gravity at their altitude. The effect is tiny, fractions of a second over months, but it is real and measurable. Imagine future humans traveling close to the speed of light toward distant stars. Time for them might pass slowly, while decades or even centuries slip by on Earth. They could return to find entire generations gone. This idea is not just science fiction. It is written into the laws of physics. The universe keeps time as a flexible thread, stretching and contracting depending on the journey. Deep space travel may someday turn time itself into a landscape humans must learn to navigate. Astronauts relearn to walk after coming home. After months spent in microgravity, the human body forgets how to balance, how to carry weight, and even how to coordinate simple steps. Bones become lighter, muscles shrink, and nerves lose practice sending the right signals. When astronauts return to Earth, they often struggle just to stand. Their legs feel heavy and unsteady. Their blood rushes downward in ways it has not for months, making them dizzy. Doctors and trainers work with each returning astronaut to rebuild strength, coordination, and confidence. Some need harnesses to practice walking safely. Others start with short sessions on treadmills before returning to normal motion. This process can take weeks or months, and it offers a preview of what humans might face on Mars or other worlds where gravity is different. Relearning to walk is not just physical, it is emotional, a reminder that our bodies are shaped and reshaped by the worlds we inhabit. Mars has storms that can last for months. Mars is a dry, cold world, but its atmosphere is full of movement. Winds can whip across the planet at speeds high enough to lift fine dust into enormous storms. These storms can start in a single region and slowly spread until they cover the entire planet. During these events, Mars becomes a hazy, muted sphere with sunlight reduced to a faint glow even at midday. The dust can linger in the air for months, clogging equipment, blocking solar power, and coating every exposed surface. During a global dust storm, the temperature swings and pressure shifts can affect everything from landers to future habitats. The dust itself is sharp and dangerous, containing toxic chemicals that can damage lungs and electronics. Living on Mars will require shelters strong enough to withstand the storm and systems that can function without sunlight for long periods. On a planet of red dust, the weather becomes a force that can reshape every mission plan. Every mission to deep space creates new medical mysteries. Space medicine is still in its early years. Doctors know how microgravity affects bones and muscles, but long-term effects on the heart, nervous system, vision, and mental health are still being discovered. Fluid shifting in the body can change pressure in the eyes, causing blurry sight. The immune system may weaken, allowing dormant viruses to reactivate. The brain may reorganize its balance circuits, leading to strange dreams or motion confusion. Even the way wounds heal could change as cells behave differently in microgravity. Each new mission becomes a human experiment, revealing hidden parts of biology shaped by Earth's gravity. Future explorers will face these mysteries with every step farther from home. The more we learn, the more we realize how deeply life on Earth is designed for Earth itself. To thrive in deep space, we may have to rethink everything about the human body. Spacecraft must shield against micrometeorites, traveling faster than bullets. Space is filled with tiny fragments of rock and metal left over from the birth of planets or broken off in collisions. These micrometeorites are often smaller than a grain of sand, but they can travel tens of thousands of kilometers per hour. At those speeds, even a tiny fragment could punch a hole through metal, glass, or the fabric of a spacesuit. To survive, spacecraft are built with layered armor designed to break up particles before they hit the inner hull. Spacesuits have reinforced plating, and external tanks or modules sometimes double as shields. Engineers track large debris, but micrometeorites are too small to detect. So every mission carries the constant risk of an invisible impact. Even the International Space Station has small craters and scratches from past collisions. Traveling through space is like crossing a cosmic shooting gallery where every spark becomes a threat. Protection becomes a delicate balance of weight, material, and design. You can watch Earth's weather systems from space. From Earth, we see lightning as streaks across the sky or flashes behind clouds. From space, astronauts can watch entire storms unfold across thousands of miles in silence. Jagged bursts of light erupt in the darkness, branching through clouds like glowing veins. Storms that seem enormous from the ground look delicate from orbit, spreading across cities or oceans as soft pulses of white and blue. Sometimes lightning strikes upward, reaching toward space in massive jets of energy. These flashes are invisible from Earth, but clear from the International Space Station. Satellites also detect rare forms of lightning called sprites and elves, which appear as gigantic rings or tendrils of red light above thunderheads. Seeing a storm from above reminds astronauts of how thin Earth's atmosphere truly is, how fragile and fleeting weather can be, and how much power moves silently through the planet without ever touching the surface of space. From above, Earth is not just a planet. It is a home wrapped in air and water, alive with motion and color. Every spacecraft has a maximum safe radiation dose. The universe is filled with invisible radiation from stars, galaxies, and high-energy particles. Earth's atmosphere and magnetic field block most of it. But in space, spacecraft are constantly exposed. Each mission calculates the total amount of radiation its crew and electronics can safely endure. There are limits based on age, gender, and length of exposure. If a spacecraft stays too long in a high radiation zone, or if a solar storm erupts unexpectedly, the risk rises sharply. Radiation can damage DNA, weaken immune defenses, and increase cancer risk. For electronics, it can corrupt memory, destroy circuits, or shut down systems permanently. Engineers design shielding, but the more protection added, the heavier the spacecraft becomes. Balancing safety, weight, and mission goals is a constant challenge. In space, the invisible becomes deadly, and every journey is measured not just in distance, but in dosage. Sound does not travel in space, but vibrations do. In the deep vacuum of space, there is no air or gas to carry sound waves, which means a scream, a roar, or an explosion would be completely silent to the human ear. Yet the universe is not entirely mute. Vibrations can travel through solid structures, allowing astronauts inside spacecraft or space stations to hear the hum of machinery, the creak of metal expanding in sunlight, or the gentle knock of someone tapping from another module. In space, sound is not a wave in the air, but a vibration in a shared surface, felt as much as heard. Even instruments that measure gravitational waves translate distant cosmic events into low, eerie tones humans can perceive through speakers. If you were outside a spaceship in a vacuum, speaking to someone through a helmet radio, you would only hear them through electrical communication, not through air. The silence of space is profound, but sound still exists in solid connections and through technology. It is silence broken only by the hum of life support systems, the buzz of your own suit, and the steady sound of your own breathing within your helmet. The first footprints on the moon are still there. When the Apollo astronauts stepped onto the moon in 1969, they left behind boot prints, tool marks, and even tire tracks from their lunar rover. The moon has no wind, no rain, and almost no geological activity to disturb these impressions. Without erosion, those footprints may last for millions of years. Even meteoroid impacts are rare enough that many marks remain completely untouched. These trails across the dust are like scattered fossils of human exploration, frozen in time. They tell a story of a few brief days when humans visited another world, leaving behind not just scientific instruments and flags, but the traces of footsteps from a world far away. Future explorers may someday walk the same ground, standing beside a footprint that has not shifted since the moment it was made. The scene is both beautiful and haunting, a reminder that once we touch a world without weather, we leave a mark that time forgets to erase. A tiny hole in a spaceship can be catastrophic. Every spacecraft is built like a sealed container, holding back the vacuum of space with layers of metal, insulation, pipes, and wiring. A hole no bigger than a grain of sand can start a leak that drains air rapidly, depressurizing the entire cabin. This is not a dramatic explosion like in movies, but a silent, steady escape that can go unnoticed until alarms detect falling pressure. Micrometeorites, or fragments of space debris, can punch tiny holes through metal walls, causing a gradual but deadly leak. Astronauts are trained to locate and patch breaches using special sealants and emergency covers. Even a drill error during construction or repair can cause a breach. The inside of a spacecraft is a bubble of Earth surrounded by nothingness. A single failure in that surface can turn the familiar air into a dwindling resource. Engineers layer walls, add alarms, and build in safety redundancy. But the threat remains. In space, the line between life and vacuum is often thinner than a sheet of paper. And now, as the final fact settles like dust on ancient stone, let the stillness of space become your own. We have drifted together through silence and shadow, through the void and the light. We have touched the surface of an existence that has no wind, no sound, no breath, only patience. For decades, humans have been reaching beyond Earth's sky, building rockets, training minds, and pushing fragile bodies into places where biology begins to fail. We have learned to float, to work, to sleep, and to dream in a realm that was never meant for us. And yet we go, because curiosity is stronger than fear, because wonder is deeper than danger. The journey to the stars is not safe. It is not comfortable. It is not easy, but it is ours. And in every breath taken in a spacesuit, in every footprint left on another world, in every silent orbit around a planet wrapped in light, we prove something timeless. That exploration is not just about reaching new places. It is about discovering what we are capable of becoming. So wherever you are tonight, whatever weighs on your mind, know this: the stars are still shining. The universe is still turning. And somewhere out there, in the silence between worlds, the next chapter of our story is waiting to be written. Sleep well, and thank you for journeying with us through the silence and the stars.